All right, so we're going to do a quick lesson on the math of chemistry. It's going to be fairly, the most basics that I can remind you of from your intro to chemistry, maybe last year, maybe the year before. So the very beginning, we're talking about significant figures. We're going to get into measurements with significant figures, and then talk a little bit later about the SI system and also density, some different conversions, and error analysis. So you can stop the video whenever you need to if you want to work out the example before I show you the answer, or if you feel like you understand everything, you can just, fast forward in the video to your pleasing. So the very beginning here is just the basics. We have to use significant figures in measurements because not every single number is accurate. Not every single number is known. So we only want to put down the numbers that we know for sure, called our significant figures, one of which is estimated. And the last digit is the estimated digit, and we'll get into that in a second. So there is always some inherent uncertainty because of that estimated digit. And we also will talk about rounding because we have to round values eventually. We can't just carry decimals out, maybe 10 decimals. That's slightly ridiculous. So we have to round, and we round at a certain time so that we don't have an uncertainty, too much uncertainty in our measurements. All right, so say we have this piece of metal here. This piece of metal is going to be measured with a couple of different rulers, a couple of different measuring devices. And each of the measuring devices has a different number of graduations. So I'll show you the difference between each of these. Let me go ahead and pull this up. So the first one has actually no graduations. It's got the ruler straight from 0 to 1 centimeters. So we have to take this and determine where that measurement lies on that big scale. And I'm going to say it's about, let's say it's about a fifth of the way. So that's 0.2 centimeters down the line. I can only write down my digits to 0.2 because there are no graduations here. Therefore, I'm going to go with one number past my smallest graduation, which is 1 centimeter. This next ruler right here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has tenths here. If it has the graduations, the smallest graduations, to the 1/10 or to 0.1, then we can measure a number, or we have to estimate a number past that. So 1, 2. That's definitely 0.2 something. This something is right here, whatever we have to estimate. So I'm going to say that's about 0.27. The 7 is our estimated digit. When we get to more fine precision rulers, something with many graduations, or many lines, smaller graduations, this one right here actually is to the hundredths place. So we have these values, which we already know. This is 0.1, 0.2, 0.3. And we also know another value that's exact, that we definitely know for sure. We definitely know for sure it's 0.2 because there's 0.1, 0.2. And then 1, 2, 3, 4, 5, 6, 7, that is 0.27 for sure. We also have to estimate. So we can estimate this next number, and I'm going to say, that looks like it's 0.2, or excuse me, 0.270. You might say 0.271. That estimated digit can vary between individuals. And then that's the example right there. The last digit is estimated. Same thing here. We have the thermometers with different graduations, different scales even. So looking at this first one here, I'm going to say that's about at 4 degrees, whatever our thermometers are measured in. But I have to give one more digit, which will be my estimated digit. So I'm going to say 0.4 degrees C. This being my estimated digit. The next one, I've got something above 8, but below 9. So I'm going to say it's 8.3 maybe. 3 is my estimated digit because that's the extra digit that I add based on the graduations of my device. The last one, similar situation. Can't see that. It's 64 due to the fact that you've got, these are in tens, so 10, 20, 30, 40, 50, 60. So then this right here will be 60 something, 63 maybe, or 64 in our case right here. That estimated digit can vary depending on who is reading that device. The reason that we have these two numbers here, is because each of these only have one significant figure. This one here has two significant figures. Now that we've added that extra significant figure, that is our estimated digit, which makes us, complete the task. If you have not heard about the Pacific and Atlantic method for significant figures, it's here. It's very, very easy. What you do is when you want to figure out how many significant figures are in a measurement, you need to count from it depends if there's a decimal present or if there's a decimal absent. So you're going to count from the Pacific or the Atlantic. So you've got the U.S., the country, the Atlantic is over here, Pacific is over here, so please don't forget that. So if your decimal is present, then you approach the number from the Pacific, P and P. If the decimal is absent, then you approach the number from the Atlantic. And then you count everything as you pass the placeholders. Placeholders are just zeros. So I'll give you some examples on the next slide, but you have to always go to the first non-zero number. Always to the first non-zero number, because that's the first significant figure. Zeros in the front are usually not significant. Zeros in the back, if there's no decimal, are also not significant figures. So let's practice. We've got this measurement. It's not a measurement actually because there's no units, so I'm going to put centimeters there to make that a measurement. If we have a decimal present, we start from the Pacific. So we start over here. Nope, nope, nope. These two are significant figures because you skip the first zeros because they are not significant. So how many sig figs do we have? 2 sig figs. The next one, decimal is present, so we're in good shape. We start from the Pacific. Nope, nope, nope. These next 3 are significant, so we have 3 significant figures. Continuing, this one there is no decimal. There's a decimal that it's absent. So we start from the Atlantic. We don't count the 0. We don't count the 0. You start with the first non-zero digit, and you continue. So there are 3 significant figures here as well. Next, we have a decimal present. We start from the Pacific. We don't count. We don't count. We start counting from here. So we have 3 sig figs here. And then we'll do the rest of these together here too. The decimal is present. You start from the Pacific. That first number is a non-zero digit, so you count it, and you count all 3. So there are 3 sig figs here. Decimal is present. You start from the Pacific. Don't count, count the 8, 0, 0. So you have 3 sig figs here. And this one, the decimal is absent. So you start from the Atlantic, but you do not count that first 0 because it's you don't start until you hit the non-zero, which is the 3 and the 4. So you have 2 sig figs here. And that looks like a decimal. That's not. This number and this number, they look really similar, but this decimal right here signifies that we know exactly that this measurement was 430 whatever. So present, start from the Pacific, and you count all 3 digits, so you have 3 sig figs here. So that's the Atlantic Pacific method. There are some different methods of counting sig figs whenever you do different mathematical calculations. So whenever you multiply or divide numbers, you have to have your answer recorded with the digits that are from the least number of significant digits in either of your values. So if we have these 2 values here, and we need to record our answer with whatever least significant figures and the total from our givens, we have present in the 3.887. The decimal is present, so we have 4 sig figs here. In the 15.5, the decimal is present, so you count from the Pacific, and there are 3 sig figs here. So it's pretty much your strong as your weakest link. Your weakest link is the 3 sig figs, so we need to record our answer here in 3 sig figs. So if you had to do that, You would start from the left, from the Pacific, and you would need to count 3 sig figs. 1, 2, 3. Well, this number right here can affect that number, that third significant figure. But in our case, that 4 is going to it's not going to affect our answer, because if it were above, a 5 or above, we'd round that 2 to a 3, but in this case, we're not going to, so it's still 60.2. And we have 3 sig figs in our answer. Adding and subtracting is a little different. You're going to have to count decimals, so we don't have to worry about significant figures in adding and subtracting numbers. We're only going to count decimals. So we're still kind of the same situation. You're as strong as your weakest link. So counting decimals, we have 2 decimals here. Counting decimals, we have 1 decimal here. So our 2 givens together, our weakest one, or the one with the least number of decimal places, is the second one, the 8.3. So our final answer needs to be recorded to 1 decimal place. So we're still going to have 12. And then whatever we need to chop this off at, we're going to chop it right there to allow for 1 decimal place. 7. And if this number here were 5 or larger, it would affect that 7, and we would round that up as well. But we're not. We're going to leave it at 12.7. Okay, so in AP Chemistry, you absolutely have to use significant figures in every single calculation. There's some flexibility on some, stoichiometry, and when you're doing dimensional analysis, so I'll tell you about that as we go. But this rule of thumb, you absolutely have to use whenever you have long calculations and when you're recording your final answers. So this is important. Look at this and read over it for me. Whenever you have long calculations and you've got maybe 4, 5, 6 steps to a long problem, each step of the calculation, carry out each answer to probably 4, 5 decimal places. And that's just going to allow you to maintain some accuracy, so too much rounding in between calculations can cause problems in the end. So you're gonna keep about 4 to 5 decimal places, and then at the end, you're done with the whole calculation, you've got a final answer with a string of decimal places. You're going to round your final answer to the appropriate number of sig figs. So look back at each step. If you multiplied, you count the least number of significant figures. If you added or subtracted, you count decimal places, and you can just do that, go back and track your decimals or your sig figs, and record your final answer to say maybe your number of sig figs should have been 3 sig figs. Well, you had maybe a final answer of 1.2345 centimeters squared, so you need to round it to 3 sig figs, so therefore that would change to 1.23 centimeters squared. So that's you going back and tracking. This is going to limit us having various different answers as a final answer because of rounding in between. Now, whenever you do dimensional analysis, when you're multiplying multiple things by each other and all you're really doing is maybe using metric conversions or only using mole ratios, these are not measurements, therefore you don't care about the sig figs there. You're going to have probably 1 sig fig on all of those. You're going to have 1 mole over 2 moles. Well, that's going to really limit your answer in numbers of sig figs if you take those into account. So do not count mole ratios as your sig figs. Do not count metric conversions as your sig figs, because those things are not important when we're talking about accuracy or precision. And if you ever have some trouble trying to figure out how many sig figs you need, use your given, whatever is given to you at the very, very beginning of a problem, and that number of sig figs can at least get you started, and that should help you complete your further calculations. All right, I'm just going to briefly show you these. We've got the SI system, which is the International System of Units. It's just a system that allows for scientists to talk in the same language, so we all use the same units, and we can all have calculations that include the same units, and it's understandable between multiple parties. So when we're talking about length, you're going to use the meter. When you talk about mass, you're going to use the kilogram, and occasionally we'll just use gram. In time, you use seconds, and Kelvin is something you'll use with temperature. We also will use degrees C, and we will not use Fahrenheit usually. We really won't much. Kelvin is our way to go here. Last one, volume. There are multiple units you can use here. You can use liters, meters cubed, which which is the same thing as a liter. It's just a derived unit because you have to multiply the meter times itself 3 times. So we also have to know the metric system. The metric system is just a series of prefixes. We're talking about the scale or the size of a measurement. And you already know the basic set of prefixes. You probably remember from biology or chemistry yourself. Prefixes are all going to be in powers of 10, which is just one movement of the decimal place. And the way that I remembered it forever, and you may have too, is King, Kilo, Henry, died by drinking chocolate milk. So you can see that these names correlate with the prefixes themselves. So you've got kilo, hecta, deca, base, which will be our base units of meter, second, let's say liter. And we've got deci, centi, and milli. Those are the basic ones. We are a little more advanced, so we use more advanced prefixes. So we have some additions. We've got, I'm going to go ahead and pull all this up here. We've got the same ones here, so kilo, hecta, deca, base, deci, centi, milli. And then we also have these extra ones. These extra ones are going to be to different exponents. So this is mega, and this is 10 to the 6th. Kilos are 10 to the 3rd. Hecta is 10 to the 2nd. Deca is 10 to the 1st. Base is just a base of 10. Deci is 10 to the negative 1. Centi is 10 to the negative 2. Milli is 10 to the negative 3, because there's like 1,000 milliliters in 1 liter. That's why those values are there. You'll see that these spaces are here. There are no prefixes that correlate with those spaces or those blank spots, but you will see that you go from 3, 4, 5, 6. So 10 to the 3, no 4, 5, but you do have 10 to the 6. Same on the back side. When you're going this way, you've got milli, then you have micro, like a micrometer. You've got nano, and you've got pico. These are working the same way in terms of decimal places. So you've got milli going 10 to the negative 3, blank spots at 10 to the negative 4, negative 5. This is 10 to the negative 6. Nano is 10 to the negative 9, and pico is 10 to the negative 10. Easily remember 9 nano. That should be easy for you. Milli, you should know, is 10 to the negative 3, so these other ones will have to be memorized. Okay, so we talked about temperature really briefly earlier. It is the measurement of the kinetic energy or the average kinetic energies in an object, and kinetic energy refers to movement and how fast things are moving. So we'll get into more when we talk about gases and other thermal properties of matter. We'll get into temperature some more. But using the Kelvin scale, this is known as the absolute scale, because absolute 0 is negative 273 Kelvin. So we'll get into that some more, but absolutely you have to use the Kelvin scale in chemistry. We will occasionally mention Fahrenheit. We will mention Celsius quite a bit, and you do need to know how to convert between the two of those and Kelvin. And one distinguishing difference here is that there is a degree symbol used in, degrees Celsius or degrees Fahrenheit, but we don't use that symbol in Kelvin. We just say K, no degree symbol. And occasionally they'll, on the AP exam, they'll take off for silly stuff like that because it's just, you're not experienced enough. So here are those conversions. If you want to go from Fahrenheit to Celsius, here's the formula. Celsius to Fahrenheit, here's the formula. Celsius to Kelvin, this is the one you will see and use and memorize. You probably already know it. So if you have a Celsius degree, you add 273 to that to get Kelvin. So if you've got 20 degrees Celsius, that's going to be 273 plus 20, so 293 Kelvin. The Fahrenheit and the Celsius, you'll see that there's some relationship here. From Celsius to Fahrenheit, you've got degrees Celsius plus 32 times 9/5 will give you the Fahrenheit, opposite on the Celsius. If you really won't do that too much, we're going to use the Kelvin and Celsius scale the most. Density is something you have learned about all your life. I'm not going to dwell on it too much. You do need to know that density is just how dense is an object, how many items or atoms are packed close together in that volume. So it's the ratio of masses to volume, so you probably remember the formula as density is mass over volume. So we will always use grams, maybe some kilograms, and you'll see various units for volume here. So you could have grams per milliliter, you could have grams per centimeters cubed, you could have kilograms per liter. It just depends on what we're going to use for different value, for different problems. So if you have a regular object, we have a rectangular prism here. If you wanted to calculate the density, you need two values. You need mass, because density is mass over volume, which we have the mass right here. And the volume is the only thing that we need to calculate. So calculating the volume, knowing that it can be various units, volume of a prism, a rectangular prism, is length times width times height. So let's say our length is 10.0 centimeters times 5.0 centimeters times 4.0 centimeters. Whenever you calculate and you get the final answer here, you're going to record it to 200 centimeters cubed, because each of these centimeters times each other will give you centimeters cubed. And then let's check our sig figs. You can barely see my decimals here. So in each of these quantities, we've got 3 sig figs here, 2 sig figs here, 2 sig figs here. Our weakest link is 2 sig figs. So we know for sure we're going to want 2 sig figs on this number. And the way you write that is in scientific notation. So you write 2.0 times 10 to the second centimeters cubed. 2.0, 1, 2. So there's 2 sig figs there. That should give you a preview to what we're going to do in just a minute. And the only reason I counted sig figs is because we multiply here. Don't forget, if you were adding, you would just count decimals. So we're not done yet. Density is mass divided by volume. So you've got 827 grams divided by a volume of, we'll write 200 centimeters cubed here for you. Sorry about the bell there. And whenever you do that calculation, you should get 4.135 grams per centimeter cubed. But that's going to be that's our tentative answer for now. We need to go ahead and use sig figs. We need to go ahead and figure out how many we need. Since this is actually 2.0 times 10 to the second, we've got 2 sig figs in the volume, and we've got 3 sig figs in the mass. So we need to record it to 2 sig figs. So we're recording that and rounding. 4.1 are 2 sig figs, and then you had to make sure that 1 was not going to be affected by that 3, and it's not here. So 4.1 grams per centimeter cubed is our density. For an irregular shaped object, we've just got to do the volume displacement method. That's really just how much water is displaced. So you take a graduated cylinder and you add your rock, for example. It makes the water move up. Whatever volume of water that it displaces or makes it move up from its original starting place is the volume of that object. So if I told you that it displaces 40 mils of water and the object weighed 20 grams, you'd say density is 20 grams over 40 mils equals 1/2 grams per mil. And we need to record this in a decimal. So 1/2 obviously 0.5 grams per mil. And then we need to check our sig figs here. So we started off with 1 sig fig, 1 sig fig, because the decimal is absent, only the 2 and only the 4 are significant. And then we end up right here with 1 sig fig. We're in good shape. Error analysis is something that everyone should be familiar with. It's only based on the fact that if your measurements are accurate, then your measurements are very, very, very close to the actual true value of whatever you are measuring. If your measurements are precise, that means you've got all kinds of measurements that are really close together. 2.2, 2.225, 2.23, 2.21. Those measurements, you're really precise in whatever you are doing, but that precision does not mean it's accurate. It could be really precise, but not accurate at all. Maybe the accurate number was actually 5. So that's just, I'll show you like maybe a basketball example. If you hit the hoop, you make the basket, you are accurate. If you hit the backboard 100 times, you're not accurate, but you're very precise. So with this question here, we've got a student collecting measurements, and each of the measurements are 19.8, 19.2, 19.5 centimeters. But the actual wire length was 25.5 centimeters. So knowing that, we can say our student was not accurate at all. Our student didn't have numbers very close to 25.5. But the student was pretty precise because each of these values were not that far off from each other. So yes, they were precise. No, not accurate. And I will ask you numerous times to calculate percent error. And percent error is based on the fact that you know the actual measurement or the actual value, and the fact that you have done some experiment and that you know your experimental value. So usually we're not perfect and our experimental values are a little bit off and they're a little different than the actual values. So this is how you calculate percent error. How much error did you have in your experiment? And take the actual value, this is known, and this is something that you did in an experiment. You say the absolute value of that, that's what these little lines are over here, and then divided by the actual value again times 100, and that'll give you whatever percent error you had. Also, occasionally, and you'll definitely see this in your textbook if you take a look at it, you'll see that sometimes error is given to you. It'll say plus or minus error of 0.5, maybe, for example. So whatever we have as our value, it'll be given to you of the plus or minus 0.005 or whatever it may be. And usually the smaller the error, the better, because you don't want to have errors in your experiment. And in that case, if it told you to calculate percent error, the error is given to you right there, divided by the value achieved times 100, and you also have percent error. So doing this calculation here, for our student measuring the 25.5 centimeters length of wire, what was the percent error of their first measurement? So their first measurement was 19.8 centimeters. You've got this value, 25.5 given to you. That's your actual minus your experimental, absolute value of that, divided by your actual value. And so whenever you do that, and I put the centimeters in there, usually percents don't ever have units, so you don't have to worry about that. Times 100, and you get actually 22%. And whenever you calculate the subtraction up here, you get 5.7 divided by 25.5. And the reason that this is 5.7 is because we're recording to one decimal place because each of our numbers had one decimal. Divided by 25.5. Whenever we do our division, we take into account sig figs. So 2 sig figs in the 5.7, 3 sig figs in the 25.5. The weakest link is the 2 sig figs. So times 100 leaves us with 22% because there are 2 sig figs in this final answer. Okay, so oops, didn't want to show you that. With scientific notation, you've been using this probably for quite some time too. We always records the first number, the integer, in a value that's between 1 and 10. So we want it to have one, that whatever sig figs it needs, you're going to be conserving sig figs, but that first number will be 1, or it can be equal to 1 and less than 10. And it's slightly different than exponential notation, but a lot of times people will just try to say they're the same thing. So whenever we have this long, really, really small number, it's really, it's tedious to try to tell you all the zeros, and someone can mess up whenever you're trying to tell them this value. So it's much easier to write it in scientific notation. So the way we get this to scientific notation is you count how many numbers it's going to take to make this decimal point locate between the 4 and the 5. So 1, 2, 3, 4, 5, 6, 7. And since it's actually going this way, we've got 4.5 times 10 to the negative 7, which shows us that it's a very, very, very small number. And actually need that right there, because there are 3 sig figs here. Next one, we've got 3.81, which is a number between 1 and 10, times 10 to the 6th. So this is a large number, and we just have condensed it for easiness, for we're kind of lazy as chemists. So this number is actually a very, very large number, with 3.8 being this point right here. 1, 2, 3, 4, 5, 6. And you relocate the decimal at the end, which gives you the 3.8 million. We've also got another small number. We write it like this for the sake of condensing the number. We've got 10 to the negative 4, so this decimal will be moving 1, 2, 3, 4, relocating there. You fill in the spot with zeros, so you get this number here. And you'll see that these numbers, the sig figs, are remaining. 3 sig figs, 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 3 sig figs. So we're maintaining our number of sig figs. We never ever cut them off. The last one here is actually telling you that you want to record your number, your scientific notation to 3 sig figs. Right here it's designating that. So let's go ahead and do that. We've got the decimal is, absent here. So if you want to, highlight or circle your 3 sig figs. So that'll be 7.50. And we need to multiply it by its number to just signify the scale of the number. So put our decimal here. 1, 2, 3, 4, 5, 6, 7. That's 10 to the 7. And very lastly, defining quantitative and qualitative. Basically, quant, numbers. These are qualities. Descriptions. Descriptions could be size, could be scale, could be color, could be smell. It's some sort of observation that you're going to be making. The quantitative are usually all measurements. They're quantities, they're numbers. Oops, it's supposed to be measurements. They're quantities, which is why you get qualitative. Quantitative. All right, so that's a review of math. Hopefully you knew 99% of all that, but it should be a good refresher. And please ask any questions tomorrow or the next day whenever you get a chance to watch this.